Malcolm, let me hand over to you to introduce Brian.
Okay, so thank you, Louis, and thank you, Penny and Boone, for organising today. So it's my pleasurable duty to introduce Brian Kennett, who needs no introduction to many of you, but possibly to some of you. So I have a little bio of him here. So Brian is someone who is very well known. He's graduated over 30 PhD students at RSES and has what I would call an encyclopedic knowledge of seismology, and is often consulted by many a student and staff member, and he will be able to tell you where that paper was published and when. So he was Google before Google was Google. Now, more focused, Brian has published his first paper 50 years ago, and it was in the IEEE Transactions of Information Theory. He started his PhD in theoretical seismology at the University of Cambridge. Since 1970, he has produced over 320 papers, 20 book chapters, and 10 books with a strongly geophysical character. His 10th book, called Exploiting Seismic Waveforms, co-authored with Andreas Fichtner of ETH Zurich, is currently in production at Cambridge University Press. He's a prolific publisher. Brian came to RSES in 1984 from the University of Cambridge as a professorial fellow in seismology. He was interim director of RSES in 1993, chair of the board of the Institute of Advanced Studies, then called BIAS, and also pro-vice chancellor of the ANU from 1994 to 1997. And of course, as many of you will know, he was director of our school from 2006 to 2010. He's received many accolades through his career, obviously, and I'll just point out some of them. He was elected to the Australian Academy of Sciences in 1994, became a fellow of the Royal Society of London in 2005. And in 2019, he was appointed an Officer of the Order of Australia, an AO. He has received numerous international medals and awards, including the 2011 Flinders Medal. It's one of the highest medals of the Australian Academy of Sciences, and the 2017 Inge Lehmann Medal from the AGU. He partially retired, if that's such a word that can be applied to Brian, in 2012, and more fully in 2016. But he's maintained an active area of research in seismology and mathematical geophysics, producing a new radial model for the Earth published only a few weeks ago, which I think will bear on his talk today. So I'll pass you on and he'll tell us about characterizing Earth structure from seismic data. Thank you, Brian.
Thank you, Malcolm. So today I will be talking about the Earth and what we can learn from seismology. And one of the fundamental issues for seismology is where earthquakes occur. But to know where an earthquake is actually located, we have to know the structure of the Earth. And to determine the structure of the Earth, we need to know the position of the source. It's a sort of chicken and egg problem. And seismology has developed on both fronts. I'm going to be concentrating in this talk about the structural aspects, and one of the limitations that used to be present was that earthquakes keep occurring in the same place. Later on, I'll be talking about how we can exploit noise sources to improve that scenario. So I'll briefly review some of the fundamentals of seismology leading into the development of structure. So the first energy that comes to you from an earthquake is a compressional wave that's like a sound wave. The next prominent arrival is a shear wave whose displacement is transverse to the path. So this is the compressional, the transverse, and then associated with the fact that the Earth has a free surface and seismic wave speeds increase with depth, there are trapped waves, surface waves, that travel along the surface, a love wave with horizontal oscillations, and a Rayleigh wave whose particle motion is much more like waves in the ocean. The surface waves spread out more slowly than the body waves, the P and S, and become the largest features on seismograms at distance. So this is what a seismogram looks like. This is at 50 degrees away from a source in Fiji, recorded in the Kimberley region of Western Australia. And I've chosen this station because it lies almost exactly due east of the source, so that the love waves appear purely on the north component, and the Rayleigh waves are later and appear on the north, on the vertical and east components. You'll see a number of different lines and colors indicating arrivals whose character is P and S. And if we're to try and elucidate what those phases actually are, we need to have an Earth model to explain them. So the major elements of Earth structure that we're dealing with are a mantle, some 2,900 kilometers thick, over a core, mostly iron and nickel, we think, and then a solid inner core. And in the mantle, we have a steady increase in seismic wave speeds with depth. And then as you go from the solid mantle into the liquid core, the compressional wave speed drops dramatically, and this has strong effects on propagation. The blue curve here is density, and the density distribution in the Earth is much less well determined than the wave speed distribution. And it represents one of the critical areas of ignorance that we have when we're trying to compare, for example, with mineralogy. So let's suppose we have a seismic event, and the one I've chosen is in Peru. If that event goes off, then we propagate P waves through the mantle. P waves that go into the core are refracted by Snell's law and return with a caustic around 140 degrees. Shear waves, on the other hand, are just a little slower than in the core, the P wave in the core, so that in fact shear waves fill up the whole core, whereas P waves don't. And that means that when we're trying to understand the structure of the Earth, we can't just look at compressional waves. We've got to know the shear distribution to understand.
Okay, Brian, we can't hear you anymore, and probably knows that by now. We'll just wait.
Okay, sounds like we have, looks like we have you back, Brian. Do you want to try unmuting? We lost you when you were talking about the S waves. And you're still muted.
Mute.
That's it?
Yeah, okay. So P waves don't sample the whole core. S waves, the S wave combination of S in the mantle, K in the core, covers the whole. So we need to understand about S to be able to see the P waves in the structure in the Earth. Now I need to go backwards here. My apologies. Skip that. So complicated wave trains travel through the Earth, and the wave fronts travel across the entire Earth. The surface waves will go around the Earth many times. And if we look at seismograms generated from them, near in, they're high frequency, complicated, further out, lower frequencies because the Earth loses energy from the waves, and we get large arrivals here, for example, the large love waves. Now, if we can look at the seismograms directly, and we see pulses like this, or in fact, we can look at their spectra, and then we are best analyzing the seismograms in terms of normal modes. These diagrams are a representation of the frequencies of normal modes in terms of wave slowness that allows one to do a direct association of the propagation characteristics and to the model. And the dark dots, the full filled dots, represent observations of modes, and the open ones are ones that are theoretically predicted but have not necessarily yet been measured. These diagrams are, a few more have been measured since I made these diagrams. The toroidal modes correspond to the love waves, the spheroidal modes to the Rayleigh waves. And a lot more complexity occurs in the spheroidal modes because P waves and S waves can propagate, and we get waves bouncing up and down inside the Earth. If we go to the normal modes at a higher frequency range, a broader frequency range, what happens is that we get to almost continuous features. Here's the region in which analysis in terms of discrete modes is a good idea. The surface waves are here, and then up in this region, basically we have body waves, which we can describe as a sum of modes or as features described by propagation path. Down in the bottom left-hand corner are the group of modes who have strong sensitivity to the density of the Earth because gravitational effects are important. And it's only a limited area of the mode space that really helps to control the density alongside the mass and moment of inertia of the Earth. Now, from those classes of information, models have been derived. One of the most important was the Jeffreys and Bullen model, started in 1930, published in full in 1940, which were tables for P and S travel times. These were found to be good, and they're still used for many years, but they didn't fit the behavior of nuclear explosions, where you knew where the source was. And so in '68, Herrin produced a set of tables for P, which included PKP tables from Bolt. But those were good, but the problem is they didn't describe everything. They didn't describe S. A few years later, Gilbert and Devonsky produced the first major new models, 1066A, 1066B, using normal modes. And then here at RSES, the work was done for the PREM, the parameterized Earth model, by Devonsky, Hales, and Lapwood. And Lapwood was Jeffrey's PhD student, and he was my PhD supervisor. So back in '75, RSES was involved in Earth models, and then the group from 1991 onwards was largely done at RSES. In 1981, Devonsky and Anderson produced the PREM model, the preliminary reference Earth model, which has travel time constraints as well as normal modes. And this has become the standard for long period seismology ever since. But it doesn't fit the travel times that well. And so in 1991, a new model, the ASP91, was produced. And then in '95, we put together a model that fitted not just P and S, but also 16 other phases. And then this year, EK137 has been created, which improves the core, and I'll explain later why that's necessary. Since 2008, AK135 has been the standard model used for earthquake location, but the Jeffreys model basically lasted from 1940 through to the early 2000s, and so it's very unlikely that any future model will last that long. What do these models look like? Now here's a comparison of AK135, the solid line, and the PREM model as the dashed line. And apart from attenuation on the right-hand side, there really isn't much to see in the way of differences. The models are very similar, but the differences are significant. One of the differences is that PREM, PEM, ES91 are parameterized models where you fix the functional dependence so that, for example, the lower mantle here in the PREM model is a single cubic in radius. Whereas in AK135, that constraint is not there. The starting point was a parameterized model, but that one has been taken away. Now, the colored areas here indicate the places where three-dimensional structure is most important. Very important in the shallow Earth, but definitely down to at least 1,000 kilometers. Strong heterogeneity in the immediate neighborhood of the core mantle boundary, certainly on the upper side and perhaps on the lower side, particularly in the region above the Taylor column through the inner core, and near the inner core boundary. And the inner core is definitely heterogeneous, but it's not as simply heterogeneous. Why do we need complicated models? Well, the answer is that the Earth's wave field is very complicated. Here is the vertical component and the transverse component of an earthquake near Vanuatu at 100 kilometers depth, recorded across the globe. A fraction of the total stations, but if you look, you can see that the major phases are picked up and identified from the Earth model. So the standard Earth models do a good job of representing the main behavior of the Earth, but we know that the Earth varies in 3 dimensions. So we now can use the information from these basic models to go to studying three-dimensional structure. Seismology's developed a whole range of ways to examine the 3D structure that's superimposed on the main radial variation. Waveform inversion is very important now for large-scale structure. Travel time tomography is still important. Studies of ambient noise are also significant. And on the long period end, the base model tends to be PREM, in the medium frequency AK135, and if you go above 1 Hertz, then really you want to use a local model because the global models are not appropriate. So if we start now to look at 3D structure, I'm showing here a display relative to the AK135 model, and the upper picture is obtained from the model S40RTS of Ritzimer and others, using surface waves plus long period body waves. The lower picture adds in high frequency information from bulletin travel time curves, which was actually completely different data. They described the same Earth, and with travel times like this, basically the travel times of surface waves, travel times of body waves, we can define high velocity structures very well. This is the structure of the Indonesian subduction zone coming through here, extending through the upper mantle and in fact ponding in the lower mantle down to around 1200 kilometers depth. Now, body wave work with the travel times, as I said, is good for high wave speed structures, but for the lower wave speeds, waveform inversion is better because it avoids problems associated with wavefront healing. A relatively recent model that exploits waveform inversion is the model of French and Romanovitz. And one of the things that they pointed out from their analysis was that the majority of slow regions, the red ones here on the core mantle boundary, tie to hotspots recognized at the surface. But there was one that stood out as different, and that's the one near the Coral Sea, where there isn't any obvious surface manifestation of a hotspot. Here's a cross section that goes through the Coral Sea region from their model, and you can see strong features associated with Samoa, Tahiti, Marquesas, and Galapagos. But here's the strong low velocity zone near the core mantle boundary beneath the Coral Sea, but apparently no connection to the surface. But there is volcanism in New Guinea and in northern Queensland, which comes from somewhere and has not moved. It's not age progressive like the rest of Australian volcanism, Eastern Australian volcanism. So Rodri Davies and I had a look at what was going on. I'll show a set of slices through the composite model that indicate that what we have is complicated structures that one can associate with past subduction that block material fast coming up from depth, and that perhaps there is some means by which driblets can get to the surface and create the surface volcanism. The lithospheric edge, a strong lithospheric edge in Australia, also contributes to producing that effect. One of the problems of the cost of waveform inversion is that you don't really want to go back and redo the work. And the group in Zurich have developed an approach which they've used in their community seismic earth model, which enables you to add in extra features to a model consistently without having to go back and do the whole inversion again. And this is one of the best ways of adding in finer scale structure on top of global structure. They start with a global model, and in fact, in parts of Eastern Turkey are down to resolutions of 10 kilometers based on the density of seismic information in that string. So waveform inversion is the way of the future in terms of 3D structure, but applied in a hierarchical way will be more effective than starting to do the whole globe again every time you want to do a new area. Now, for many years, seismologists regarded noise, particularly the microseisms of sea, as a nuisance. In fact, the early systems were photographic, and you had a high frequency system sitting here and a low frequency system sitting here, avoiding the microseismic peak because you couldn't do anything useful with it. But now we can exploit the microseisms, the seismic hum at low frequencies, and even cultural noise at different scales, because what we can do is to cross-correlate signals at different stations, and that gives an approximation to a source and a receiver at the stations. So I'm showing here some results from Bouet et al., who took stations across the globe, cross-correlated them, and then the left-hand panel was a days with no major earthquakes. And what you get from the correlation is something that looks rather like the standard wave field. It's not exactly the same, but it's very close, and all the major phases are represented. But on the days when there were strong earthquakes, things changed. Stronger core phases, SCS appearing on the vertical component, which is not expected, and other features like this one, whose time relations simply are not those of expected seismic phases. The work by Tanshong Pham and Hrvoje Chelčić started to cross-correlate coda of large earthquakes across many stations. And you can view each of these stations as being a source with and receiver pairs. And this means you can build up a record section across the whole globe. What's being done here is looking at the late times, 3 to 10 hours after a big earthquake. And you create an image here from 0 to 180 degrees. And the top panel is observations. The lower panel is synthetics, based on the AK-135 model. And the first thing that strikes one is they're remarkably similar. The second question is, why do we have these features? There are many features that correspond directly to expected waves. This is, for example, a wave that goes through the core twice, but there are others with behavior like this that simply are not a regular part of the wave field. What we managed to work out is that everything in these pictures comes from the interference of phases. Everything you see that even looks like a regular phase is actually created from the difference of other phases that have interfered. And once you have that information, it enables you to interpret and go on to look for other features of the wave field. Now, I mentioned the inner core at the beginning, and the inner core is solid, and people have looked for many years for the shear wave that would travel through the inner core. But by looking at the cross correlations of the coda, it was found that there are features in the wave field that are sensitive to the wave speed in the inner core, and Chelčić and Pham found a best fit between the observations and the calculated seismograms for these scenarios when you reduce the shear wave speed in the inner core by about 2.5% relative to the standard values. So by looking at an indirect observation of the Earth, which does not use the earthquake sources, we've been able to learn something about the very interior of the Earth. An area which will become more important is the use of noise for both sources and structure. And this is a first pass demonstration of principle achieved by the group in Zurich, where they have taken noise sources, or they've taken the noise and they've tried to invert it to get both a distribution of where the noise is and the seismic wave field. This is for the 3 months of the Northern Hemisphere winter, showing strong noise sources in the Northern Pacific and the Atlantic, and also some down here in the Southern Ocean. The sensitivity to structure is concentrated between a pair of stations. The sensitivity to the sources lies on the outside, and this can be exploited to produce the effect of separating source and structure. And I believe we will see more efforts in this direction because there is the potential of getting truly global coverage, not conditioned by earthquakes. Now, I earlier mentioned that we can explain most of the major phases across the globe seen on seismograms with pretty well with a global Earth model like AK-135. So why am I been looking in recent years at trying to update that model? Well, the answer is new observations came in of the phases which are S wave in the mantle, then P wave in the core, the red ones here, that are bouncing on the underside of the core mantle boundary. If there's a single bounce, this is SKKS. There's a double bounce, S3KS, and we start getting these complicated core sticks developing. The picture for S4KS is very pretty, but difficult to interpret, and any more is almost impossible. These phases can be observed with, particularly on the paths from deep earthquakes in Tonga, Fiji to Europe. And the observations, when compared with the predictions, for example, with the PREM model, show that if we look here at S5KS, here's the predicted time, it's not matching the observations. So something has to change at the top of the core. And with the various groups have looked at these phases, and what we find is that the PREM model is too fast, and the AK-135 model is too slow when we look at the differential times between different multiples. That means that the structure at the top of the core needs to be changed to be slightly faster than AK-135 and slower than PREM. But you can't change one part of the Earth without having to change the properties of the other parts if you want to fit all the phases. And so you have to adjust the lower mantle as well as the outermost part of the core. And through a sequence of a couple of hundred models or so that I've tried, we managed to find in the end one that does a reasonably good job. This is the model EK-137. The numbers represent a construction process where you give yourself room to give yourself extra numbers. EK-137 has some relation to AK-135, particularly in the mantle, but the EK series were derived from a velocity structure in the core, epoch V, which was produced by fitting an equation of state with the Vine equation of state and the final model is simple enough. It can just different. It's slower than PREM, it's faster than AK-135, and you still manage to fit 18 major seismic phases. But this is a complicated trade-off, and it was not simple to achieve. The other feature that's been introduced into this model is the slower inner core. You can see it's not a big change, but then the inner core velocities are not large. So the new model also resolves a minor problem in previous models with the bulk sound speed. With the gradient of the bulk modulus was wrong in this neighborhood, and that's now fixed. So a new model is there, which hopefully will be better for core studies, but would not make much difference to people studying the mantle. Now, when one studies the Earth and one looks at the three-dimensional variations, one of the aspects that is frequently missing is how do we link the seismological distributions to the properties of measured minerals. Most seismic images are of one wave type, just the shear waves. So like the right-hand one here. But it is possible by jointly inverting P waves and S waves, in this case it's travel times, to get information on the bulk sound speed, that's the sound speed associated with the bulk modulus, as well as the sound speed associated with the shear modulus. And this is the most important, I think, place to be. The reason people have concentrated on the shear wave speed is you can cover the globe more effectively. But with waveform inversion, it's theoretically possible to extract P waves as well as S waves. And that's an important thing to do. The S waves show up things like subduction zones much more strongly than the bulks, the bulk modulus variations. And this says something quite interesting about the nature of what's going on in those slabs. Stagnant slabs, for example, have a stronger bulk modulus signature than those that penetrate directly. So there hasn't been as much progress in terms of joint inversion for P and S velocity as I might have expected, but I believe it is something that's very important for the future. Now, if we start with thinking about the bulk modulus and shear modulus, we can actually look at some other phenomena which we know are likely to be important. Iron-bearing minerals in the lower mantle are expected to undergo a transition under pressure in which the iron atoms flip from a high spin to a low spin state. And the measurements that have been made of this effect, particularly at low temperatures, show a very large effect on the bulk modulus and less on the shear modulus. The group led by Marquardt, now at Oxford, have demonstrated some rather dramatic effects on the bulk modulus. These get muted as the temperature increases, so that if you were on a trajectory through the Earth you would not expect an enormous variation. But is there any sign that such features actually exist in seismic models? The answer has been no. But let me try and convince you that there may be a mild signature left in seismology. If we take the bulk modulus and the shear modulus, then there is a semi-empirical property that the shear modulus divided by the bulk modulus plotted against the normalized pressure, that's pressure divided by bulk modulus, is essentially linear. There is a theoretical argument by Stacey and others that suggests this should be true, but in practice, the best evidence is that many materials, this is a pyrolite model from Steve Gruer in Hime University, and many other materials do give you a virtually linear behavior as a function of pressure. And the only slight deviations here come from where garnet is being eliminated. But if we look at the situation with a spin transition, you follow a roughly, this is from the Marquardt experiments, you follow a roughly linear trend, and then because the bulk modulus goes berserk, you fly off the diagram and then eventually come back and stabilize again in another trend which is associated with low spin. So in the case of a spin transition, you can expect two slopes and a transition region in this same plot of bulk modulus, shear modulus to bulk modulus and normalized pressure. There's some ab initio results from Bridgmanite, from Shukla, Benchkovitz and others, which are useful because they illustrate the situation when the spin transition is present or suppressed. And in that case, what you're expecting, and because these calculations were done along a mantle geotherm, is that you would get something roughly linear, transition, and then roughly linear again. Now, if we look at the lower mantle models, this is the difference. The upper one is the PREM model. The lower one is the AK135 with EK135 at 7 on top. There's a very significant difference. PREM cannot have an effect in which there can be a change in the slope because it's a single cubic representation in radius for both bulk modulus and shear modulus, AK135 is flexible, more flexible, and I noted a number of years ago that this looked like two separate segments. What I think is happening here is that we are seeing a mild transition remaining after three-dimensional averaging to get a radial Earth model that it is representing the high spin to low spin transition. It remains to be seen whether the referees of the paper believe me. If we have variations that include the effect of the spin transition, they'd be expected to occur between these two radii in the Earth. So now here I've constructed a model for the modulus ratio. It's a linearized model, so it's combining the results of the bulk sound speed and shear wave speed you've seen before. And this is dominated by the shear wave speed. At this point, the correlation in this interval, the correlation between the bulk sound speed and shear waves weakest, and it seems as if what we've got is fairly rapid variations that, when they average, allow a small but distinct imprint to be retained from the spin transition. So in this survey, I've tried to take you through from the beginning to radial structure to 3D structure, and to try to relate it back to other things like mineralogy. Seismology is one of the fundamental tools for the globe, but it needs to be complemented by experimental techniques, because we simply can't get to everything from the surface. Thank you.
Thank you, Brian. There's lots of applause coming through in the form of little symbols, but that's the best we can do. Okay, so those who would like to ask questions, I will, well, if you please use the participants window to raise your hand so we can do this in a orderly fashion, or if you don't have a microphone or don't wish to speak, please type something into the chat and let's see how we go. I've got one in the chat from John Menzies. Any thought on the implications for the age of the core? Inner core? You can answer that question directly if you wish.
Okay, I mean, I don't think seismology can help. We know it's there because we can see what it looks like today. Paleoseismology is just possible at the surface, but for the deep Earth, there's no indication of age at all.
Okay, we've another question. Thomas, would you like to unmute and go ahead?
Yes, sure. Can you hear me?
Yeah.
So it's a very simple one, but I recall that from the French and Romanovich paper, they had this 3D structure, like an isocontour, to illustrate how the Howling plume was looking in the model. So I wonder if you have a similar image to have a look at the Coral Sea, where maybe you could have a contour for the plume potential and a contour for the subducting slab in 3D.
Let me try to find the in this case, you can take the zero line as being your best separator between subduction remnants, which are blue, and material which is lower wave speed and presumably, but not necessarily, hotter. So here is a feature in the neighborhood of the Coral Sea that goes down to of the order of 600 kilometers deep, and if I showed you the cross sections going east-west rather than that, you would find that this is in fact ponding up against the sharp edge of the cratonic lithosphere in northern Queensland. But in an image like this, the best you can do is to draw a line, and the zero perturbation against the AK-135 background is as good as one can draw.
Okay, and if I may just quickly, what are your thoughts on the recent studies that suggest destabilization from you know, ponding slab, that this destabilization could lead to enhanced water content at shallow depths and could potentially trigger melting? Do you think that this can be related in any sense to what you see on your slices here?
The pieces of subducting lithosphere here would have to be many of them 20 million years or so old. It's not young, it's not a new, they've been around for a long time. And any material coming up from depth has got to find its way through a maze. There's 3 layers of material which have been subducted from different directions. Very hard to disentangle the different effects.
Okay, thank you.
Okay, we've got one quick one from the chat, which we have to interpret as well, Brian, which is, what spin velocities are usually expected?
Okay, in terms of the spin state, we don't know. Basically, the statement everyone's made is there's no evidence in seismology for the spin transition. Most people have looked at the PREM model, which cannot show it. It's as simple as that. The difference between the PREM model and AK-135, BK-137 in this case, is a possible sign that we have a spin, residual spin effects. So basically, we would expect there to be effects, particularly in ferropericles, not much in bridgemanite. And these then, when you produce your radial Earth model, you are averaging over 3-dimensional structure. If there is a consistent signal, it can survive. But if by looking for P waves alone or S waves alone, or one modulus, it's less easy to find than looking at the ratio between the bulk modulus and the shear modulus.
Hello, I'm Sun. I have a question. So I realized that in some recent study, they point out that there is a need to modify the P wave velocity at the base of the outer core, which is the air layer. So my question is, why you don't take them into account? Is there any particular reason for not taking them into account in the newest model EK-137?
Because the big problem for the inner core, I mean, it already took into account the differential times basically for waves going through the inner core. The problem there is the anisotropy of the inner core is significant, and in effect, if you make different choices about how you represent the average structure, you change the structure near the core mantle boundary. I looked at this very closely when developing the new model and felt that as a representation of 1-dimensional structure, as opposed to a full representation of 3D structure, it was difficult to do better. Which isn't to say you can't, but it's very difficult to make such changes and preserve the fit to all the different phases.
Thank you. Malcolm, you want to go next?
Yeah, Brian, in the middle part of your talk, you mentioned the cross correlation of earthquake coda and showed some unique new observations that we're seeing now that are not in the seismic wave field directly. Can I just ask you to speculate sort of future of where do you think in the earth we will learn the most in terms of exploiting these new types of data set compared to what we've had in the last 50 to 100 years?
Well, the first place that we've got effects are in the waves that travel nearly vertically, up and down, multiple bounces in between surface and the middle of the earth. Though that's been the first sign. I have a feeling that the next place will in fact be to pin down things like outer core, but basically the links between outer core structure and mantle structure. The mantle can be well studied by other means. The core, you need all the help you can get.
Okay, and we've got, maybe we'll just do this as the last of the formal questions session. There's one in the chat, which is, I'll read this out slowly, to delineate the geometry of slab and or plume, how many perturbations, for example, 1% or more, are reliable to interpret these structures, and which velocity structure is more reliable, P or S?
Right, let me come back to this. This one will do. Sure, I need to get to the picture. But, intriguingly, for some, determining the edge of a perturbation is a matter of judgment, and certainly if something is a couple of % fast, since tomography tends to underestimate real numbers, you've got signs of some real change. Most people would say that the best definition of subduction zones comes from P-wave tomography because there are more observations. Interestingly, although S-wave observations can be noisy, the perturbation effects on travel times are bigger. And so the best images that I've succeeded in producing have come from S-wave travel times, not from P-wave travel times. That doesn't mean to say that is the best, that's just the best I've achieved.
All right, thank you. I think we have an opportunity now to sort of take a step back and thank Brian once again. And if there are any of the sort of student cohort or early career cohort who would feel more comfortable asking questions of Brian outside of the formal process, this would be your opportunity. So thank you, Brian. I shall stop